I want you to picture a wolf, a real wild wolf.
Okay.
You know, gray fur, sharp eyes, standing there in the snow, maybe looking a little menacing. Got it.
Got it.
Okay, now picture a husky. Maybe it's in someone's backyard. It's got the same pointy ears, the same snout, similar fur.
Right. To the untrained eye, they can be really tough to tell apart.
Exactly. So imagine you have this state-of-the-art supercomputer. You spend millions, you feed it thousands of photos, and your goal is simple. Tell me, is this a wild wolf or is this a domesticated husky?
And this is a real experiment. It's like the classic hello world for computer vision. And at first, the results were amazing. The model was just nailing it.
High accuracy. It looked like a total success.
A huge success until the researchers decided to, do a little audit. They wanted to know why it was so smart.
What was it actually looking at? The eyes, the fur.
And that's where the oops moment happened.
Yeah.
It turns out the AI wasn't looking at the animal at all.
It was looking at the background.
Exclusively the background. If there was snow in the picture, the computer predicted wolf.
And if there was grass or a fence,
it predicted husky.
So they didn't build a wolf detector, they built a snow detector.
Precisely. And that story is the perfect entry point for today's deep dive.
Yeah.
We are digging into neural networks, deep learning, and decision trees.
And we're going to see how we moved from, manually teaching computers to see to these black box systems that learn on their own and sometimes learn completely the wrong thing.
And we're going to get into the actual math.
We are doing calculus on a podcast.
But I promise it won't be painful.
Not at all. So before we get to the math, let's set the scene. Before deep learning became this huge buzzword, how did we even try to solve this problem?
Well, we used what's called manual feature design. This was the way for decades. If you wanted a computer to recognize a bicycle, you, the engineer, had to mathematically define what a bicycle looks like.
Which sounds simple, but a computer just sees a grid of numbers, right? It doesn't see wheels or handlebars.
Exactly, it just sees pixels. So engineers use tools like something called ImageHog.
ImageHog.
Like the animal.
Spelled H-O-G. It stands for histogram of oriented gradients.
Okay, unpack that for me.
A gradient is just a change in brightness, from a dark pixel to a light one. It means there's probably an edge there.
Yeah.
So ImageHog was code that looked for edges oriented in certain ways. You literally tell the computer, if you see a sharp curve here and a straight line there, that's probably a handlebar.
I see. So you're micromanaging the machine. You're trying to hard code reality.
And reality is messy. That's the problem. What if the bike is upside down? What if it's rusty? The manual approach was just incredibly brittle.
And the data shows that, right? I was looking at the charts from the ImageNet competition.
Right, ImageNet. Think of it as the Olympics for computer vision. And between 2010 and 2011, the error rates were just stuck. They were hovering around 50 to almost 80%.
That's not great. That's barely better than a coin flip.
We hit a wall. We just couldn't describe the world fast enough for the computer. And then 2012 happened. The chart just drops off a cliff.
That's the turning point. A team used a deep neural network. They stopped trying to define the features. They just fed the raw pixels into this network and let it figure out what mattered.
And the results?
The error rate crashed. By 2014, it was down to around 7%.
That is a staggering drop in 2 years.
And we saw the exact same thing in speech recognition. On the Team8 dataset, error rates were flat for a whole decade, 2000 to 2010. Then deep learning comes along, and the errors just fall off a cliff there, too.
So the big shift, the world-changing idea, was moving from, I will tell you what a wheel looks like, to here are a million wheels, you figure it out.
That's it. The network learns its own features. It builds its own hierarchy of patterns.
Okay, so let's open up the hood. What is this structure? We hear neural network, and we think of, like, a glowing brain in a jar.
It's really just a stack of math. But the brain analogy is useful. You have an input layer, your image, an output layer, your decision, wolf or husky, and then in between, you have these hidden layers.
And this brings us to a concept that I found pretty mind-bending, the universal function approximator.
It's a very powerful theorem. Basically, it says that a neural network with just 2 layers, if you give it enough neurons, can mimic any continuous relationship between an input and an output.
Wait, any relationship?
Any. It doesn't matter how complex. If a pattern exists, this structure can mold itself to fit it. It's like a piece of clay that can take any shape.
But hold on. If it's just layers of math, aren't we just doing linear algebra? Like if I multiply a number by 2, then by 3, I could have just multiplied by 6. Stacking straight lines just gives you another straight line.
That is the crucial insight. You nailed it. If it's all linear, You don't learn anything complex. You need a spark.
A non-linearity.
Exactly. We call it the activation function. It decides if a neuron fires. In the early days, we used the sigmoid function. It's that S-shaped curve that squishes any number between 0 and 1.
Which makes sense for probabilities, but we don't really use that much anymore in the hidden layers, do we?
Not so much. The real workhorse of modern AI, the thing inside ChatGPT and these huge vision models, is something called ReLU.
Rectified linear unit. It sounds incredibly high-tech.
It does, but it's shockingly stupid. The function is just, if the number is negative, make it 0. If it's positive, leave it alone.
That's it. That's the magic.
That is it. It's basically an on-off switch. The formula is just max 0, z, wizzy. But that simplicity is its power. Because it's so fast to calculate, we can stack thousands of these layers. It adds just enough of a bend to learn complex patterns.
So it turns off the noise, lets the signal pass through.
Exactly.
Okay, so we have the structure. Layers of neurons with these little ReLU switches. But how does it actually learn? Because when you start, all the connections are just random numbers, right?
Complete random garbage. An untrained network will look at a wolf and predict toaster.
So how do we get from toaster to wolf?
Two big ideas: gradient descent and backpropagation.
I like the visual for gradient descent. You're on a mountain range in the dark. You can't see the bottom.
Right. Your goal is to get to the lowest point in the valley where the error is 0.
So you feel the ground with your feet, find which way is steepest downhill, and you take one step. Then you do it again.
That's gradient descent.
Mm-hmm.
But you pointed out the problem. A neural net has millions of knobs or weights to turn. It's a million-dimensional mountain. How do you know which of a million directions is down?
And the answer is calculus.
Specifically, the chain rule, through a process called backpropagation.
Okay, this is it, the math part. We're going to walk through the example from the notes because it makes it so clear. So let's say we have a tiny function with two weights, $W and 2W2.
And that function is GW2, AGW equals W2 plus 3W on W2.
Let me say that again. That's $W cubed times 2W2 plus 3 times 2W.
Correct. Now let's just pick some random starting weights. Say $2 and 22 is 3. First, the forward pass. We just plug in the numbers.
Okay, I can do this. 2W is 2 thrills, so 2 cubed is 8
Mhm.
times $2W, which is 3. So 8 times 3 is 24.
Got it.
Then we add 3 times $2W, so 3 times 2 is 6. Add them up. 24 plus 6 is 30.
Perfect. The output is 30. Now for the magic. The backward pass. We want to know if I just nudge one of these weights a tiny bit, how much does the result change? We're measuring sensitivity.
Which one is the big lever? $W or $20 esteem?
Exactly. This is the derivative or the gradient. Let's look at the $W way. Using the calculus power rule, the derivative of that first part, $13.22, becomes $3, $2, W12, W22.
Okay, let's plug in the numbers. So that's 3 times 2 squared times 3.
Right.
3 times 4 is 12, times 3 is 36.
Good. So the first part has a sensitivity of 36. The second part of the formula was just plus $3W1. The derivative of that is just 3.
So you add them. 36 plus 3 is 39.
That is our gradient for W $39.
Okay, stop there. To me, that's just a number. But what does 39 scream to the computer?
It screams that W is incredibly volatile. It has huge leverage. For every tiny step you take with W, the output gets magnified 39 times.
That's a massive lever.
It is. Now compare that to W2. If you run the math for W2, its gradient is just W33, which is 8.
So $W has a sensitivity score of 39, and $2 has a score of 8.
Exactly. So the network says, aha, if I want to fix my error, I get way more bang for my buck by changing W dollars. It knows exactly which knob to turn.
And it does this for every single connection, all at once.
Billions of them, all at once. And of course, we don't do this by hand. We use software like TensorFlow or PyTorch that does automatic differentiation. It just zips backward and calculates all these gradients for us.
And that's what let us build things like GPT.
Without backpropagation, we'd still be stuck trying to define handlebars by hand.
So that's the neural network, the powerful, calculus-driven black box. But the source material contrasts this with something completely different, something you can actually read. Decision trees.
Yes. If a neural net is a black box, a decision tree is a flowchart. It's totally transparent. Think of it like a game of 20 questions.
You start at the top and ask a question. Like, is it an animal? Yes. Does it bark? Yes. Is it a husky?
Exactly. The whole goal is to split your data into cleaner and cleaner groups. And to pick the best question, we use a concept from information theory called entropy.
Right. When I hear entropy, I think of chaos, disorder.
It's very similar here. It's a measure of impurity or uncertainty. A bucket of balls, mixed 50-50 red and blue, has high entropy. You have no idea what you'll pick.
And a bucket of all red balls
Has zero entropy. Total certainty. The goal of a decision tree is to ask the one question that reduces entropy the most. We call this information gain.
So the computer looks at every possible question. Is it red? Is it round? And it picks the one that separates the red from the blue the best.
Spot on. It's greedy. It always picks the question that cleans up the mess the most.
But there's a trap here. It's the same one the neural networks face, just in a different form. Overfitting.
Ah, yes. The bane of every data scientist. This is the student who memorizes the answers for the test but fails the final exam.
Because they didn't actually learn the concepts.
Exactly. A tree can ask too many questions. It splits and splits until it has a perfect rule for every single example in your data. Like, if it's green, round, has a dent, and it's a Tuesday.
Yeah.
Then it's an apple.
Which is useless in the real world. That rule is modeling the noise, not the signal.
Right. So with decision trees, we have to do something called pruning.
Literally cutting the tree back.
Just like gardening. We chop off the branches that are too specific. We use statistical tests, like the chi-squared test, to ask, is this split actually meaningful, or did we just get lucky with this data?
And if it's just statistical noise, you snip that branch off.
Exactly. You sacrifice a tiny bit of accuracy on your training data to get a model that actually works in the real world.
So we have these two amazing approaches, the powerful black box neural net and the logical, transparent decision tree.
Both have totally changed the world. We've gone from manually defining bicycles to systems that can drive cars.
But, and there's always a but, we have to circle back to our snow-loving wolf.
The husky versus the wolf.
The math worked, the gradient descent found the bottom of the valley, and the model failed.
It failed because it was efficient.
Efficient.
Neural networks are lazy. They are pattern matchers. They don't have common sense. They just found the easiest, strongest correlation in the data set. That was snow equals wolf.
Correlation does not equal causation.
And the machine doesn't know the difference. This is the danger. Whether it's a decision tree or a deep neural net, you have to verify what it's actually learning.
Because if we're using this for, say, medical diagnoses or loan approvals.
Exactly. If an AI denies your loan because of the background color of your ID photo, that is a snow detector problem. It found a correlation that isn't a cause.
It's a fascinating thought. We're building these tools that are mathematically proven to be able to learn almost anything, but we can't always see the why.
That's the challenge for the next decade. Not just building accurate models, but building trustworthy and interpretable ones. We need to know when the machine is looking at the wolf and when it's just staring at the snow.
So the math works, but it still requires human vigilance. Something to mull over before you ask Siri your next question. Does she actually know the answer, or did she just find a really good pattern in the noise?
A very valid concern.
That's it for this deep dive into the neural revolution. Thanks for listening.